Hi, welcome to Backer Breaks It Down. In this episode, we're going to look at functions and function notation. So, functions. Every single math class, we talk about functions. What is a functional relationship? How do you know if a relationship between two quantities represents a function? It's a good question, right? And so, any relationship involves two quantities. You've got the input, which is usually the value that's given first in a relationship, and the output is the second value. It is what results. So when like the input goes through the relationship and the result is the output, is essentially like the relationship between the two. A function is a very specific relationship, and it's a correspondence between an input variable and an output variable that assigns a single output value to each input value. Okay. So what that means is that like any given input value has exactly one corresponding output value. Okay. Now, when you identify a relationship to be a function, we can then say that that input is the independent variable, and we can say that the output is the dependent variable. Okay, but that's if it is indeed a function. So let's actually take a look at some relationships and determine whether or not they are functions by definition. Okay, so just remember that in a function, any given input value has exactly one corresponding output value. So, like the first thing that you can look at, so there's like 8 relationships here. The first thing I'm going to look at is the inputs. All right. So in A, notice that all of my inputs, I have 5 of them, but they're all different. That is an excellent indicator that what we have here is a function. Okay. If all the input values are different, it's definitely a function, because what that means is that all the corresponding output value, like there's only one. If all the inputs are different, then there's only going to be one corresponding output value. So like that is good. A is definitely a function. If you look at B, notice that the input of 8 is repeated. And so because it's repeated, like I'm like, oh, this is not a function. I'm just going to verify that it's not a function, because I'm going to look at the output values. So we have an input of 8 with an output of 0, an input of 8 with an output of 1. So right away, 2 different outputs for the same input. So like that one is definitely not a function. So let me just write down our findings here. I'm going to use a star if it is a function, and I'm just going to write not if it isn't one. Okay. So if you've got no repeating inputs, that's a really good indicator that you are like looking at a function. If you do have repeating inputs, just verify, like look at those corresponding outputs, because functions can only have one corresponding output. Okay. So looking at the mapping diagram in C, like if I'm just looking at the blue inputs, I'm like 1, 2, 3. Oh, no repeats. But those arrows kind of tell us like what each input goes with. So the input of 1 has an output of 8, and the input of 2 has an output of 9, and the input of 3 has an output of 10, but also has an output of 11. So right here, this is telling me that this is not a function, because in a function, any given input has to have one corresponding output, and that input of 3 has 2 corresponding outputs, and that's just not allowed. Okay. Now, when it comes to graphs, I think graphs and determining whether or not they are functions, that's like the one thing that I think we all do very well. Because we have something called the vertical line test. And if the vertical line goes through more than once, we know it's not a function. And the reason for that is because if it goes through more than once, what that indicates is an input that has more than one output. So if you look at the 5 on our graph, the input value of 5 has an output of 4, but the input value of 5 also has an output of 5, and that's not allowed. So the vertical line test is just a visual interpretation of, in a function, any given input has to have only one corresponding output. All right, so we just determined that that graph is not a function. It fails that vertical line test at 5 and also at 7, in case you're like, hey, doesn't it do that same thing at 7? What we have in E and F, these are sets of ordered pairs. And so once again, I'm going to look at my inputs. And if I notice that my inputs are all different, then it's like, ooh, that is most definitely a function. Okay. If I see any repeats, like if I'm looking at the relationship F and I notice that that -1, we have a repeat. So you have -1 with an output of 0. You have -1 with an output of 1. So right there, it's failing, basically what makes a function. So that is definitely not a function. In G and H, we're looking at some verbal rules. Okay, so you might have to think a little about these. But remember, in a function, any given input has exactly one corresponding output. So G says each radio frequency, X, and a listening area has exactly one radio station, Y. So I don't know if you guys even listen to the radio anymore. But I listen to the radio every morning when I'm driving to work, and I listen to 98 KUPD, and it has a frequency of 97.9. Yeah, but they go by 98 KUPD. I know they round up apparently. Okay, but what I'm saying is that's the frequency, and when I dial into it, I always get KUPD. I don't get another radio station, making this scenario a function. Okay, now if I dialed into 97.9 and I got something else and I got KUPD, I don't even know how that would happen, but then it wouldn't be a function. H says the same television station X can be found on more than one channel Y. So ABC, that's a network. Okay. And if I tune into ABC and I find myself going to channel 7, but then someone else tunes into ABC at my house and that's on channel 12. Okay. That's kind of what H is saying. And it's well, that isn't a function by the mathematical definition because the input of ABC has two different corresponding outputs, two different channels that I can find it on. So that would make it not a function. So yeah, the verbal descriptions you might have to think a little bit about in order to ascertain whether or not it is a function. So now function notation. Okay. So on your screen right now, I have standard notation, y equals 2x plus 5, and I have function notation, f of x equals 2x plus 5. And I don't know about you, but I think it's kind of obvious here. What do you notice? What do you wonder? Well, it's I notice that the difference is in the standard notation, they're using y, and in the function notation, they're using f of x. And then I wonder oh, so that's just the same? Yeah, it's I like to think of function notation as just fancy notation. Okay, so f of x is representing the output value corresponding to a given x, and x is your input variable. So if you look at this diagram here, they're saying f is the function name, x is your input variable, and then the rule, that's what to output. So function notation is just a fancy way of writing y. Okay, and that's all it is. So in this example here, we're going to explore a function, it's a contextual verbal function relationship. We're going to talk about our independent and dependent variables, and then we're going to do some interpreting of function notation. So if you work for an hourly wage, your gross pay is a function of the number of hours you work. So there are two quantities involved here. You've got your gross pay, and you've got the number of hours you work. These are your two variables. One of them totally depends on the other. Okay. So the independent variable and the dependent variable are your inputs and outputs respectively. Okay. It's just when you have a functional relationship, that's when you see these terms independent and dependent. But your gross pay is definitely the one that's dependent on the number of hours you work. So that would mean your gross pay is your dependent variable, and then the independent variable is the number of hours. Okay. Now, if you earn $9.50 per hour, it says complete the following table. Okay. So if I'm making $9.50 an hour and I don't work any hours, like my gross pay is going to be zero, right? Obviously, although I would love to make money for doing absolutely nothing, but yeah, that's not going to happen. Now, how would I figure out how much my gross pay would be if I worked for 3 hours? You're right. I would just have to do some multiplying. So 950 times 3 and so on. And that's how I would complete the table. Okay. And so like I already did that here. Part C, it's like write a sentence explaining the meaning of f of 10 equals 95. So I wrote a sentence. I'm like, if I work 10 hours, my gross pay is $95. So basically when you are interpreting function notation, you want to like go back and you want to tie the numbers to your independent and your dependent variables. So the 10, you see how the 10 is like inside the parentheses here? Well, that means since it's on the inside, it's the independent variable. So that's why I'm saying 10 is the number of hours I work. And $95 is my gross pay. Okay. But that's functions and function notation in a nutshell. So when you're identifying functions, you want to look and see, does any given input value have exactly one corresponding output value? That's what you're looking for when you identify functions. And that's how Backer breaks it down.